Welcome to today's practical. Get your lab coats on and your safety goggles ready, because we're about to explore how different surfaces interact with infrared radiation. You might have noticed how certain materials, like a shiny silver kettle, don't feel as warm as a matte black radiator, even when both are exposed to the same amount of heat. In our previous lessons, we highlighted how this happens because different surfaces absorb and emit heat at different rates. But how can we measure this? That's exactly what we're going to do today, using a simple but effective tool called a Leslie cube. Before we jump into the experiment, let's take a moment to appreciate why this experiment matters. It's more than just an academic exercise. Understanding heat transfer is essential for solving practical problems. Firstly, this experiment relates to energy efficiency. Engineers and architects use this knowledge to design buildings that retain heat in winter and stay cool in summer, saving energy and money. Next, think about your everyday choice of clothing. Why does a matte black t-shirt feel hotter than a shiny white one on a sunny day? This experiment sheds light on the physics behind these experiences. Finally, even in extreme environments like space, surface coatings are designed to manage heat radiation, ensuring spacecraft stay within operational temperature limits. Our goal is simple yet powerful: to investigate how the amount of infrared radiation emitted by or absorbed by a surface depends on its properties. To do this, we'll need a Leslie cube, which is a metal cube with 4 different types of surfaces: matte black, shiny black, matte white, and shiny silver. A heat-proof mat, a kettle to produce boiling water, and an infrared detector to measure heat produced. Now let's go through the process step by step. Begin by placing the cube on a heat-proof mat to protect the table. Carefully fill it with boiling water, almost to the top, and replace the lid. The hot water will heat the walls of the cube evenly. Next, let the cube sit for a minute. This allows all 4 surfaces to reach a steady temperature. Think about how the heat is being conducted through the metal to the surfaces. This is crucial for ensuring a fair comparison. After a minute has passed, take the infrared detector and hold it at a consistent distance from each surface. Measure the intensity of radiation emitted from each side in turn. Keep the distance exactly the same each time. This is because if the detector is closer to one surface, it will record a higher value, even if the surface isn't emitting more radiation. Next, write down the intensity of radiation for each surface in a table. Here's an example of what these results might look like. These numbers give us a snapshot of how well each surface emits infrared radiation. Matte black is clearly the best emitter, while shiny silver reflects most of the radiation and emits very little. Now that we have our results, let's dig deeper. Specifically, let's create a bar chart with the surface types along the x-axis and the infrared intensity on the y-axis. This makes it easy to see which surfaces are the best and worst emitters. With this data visualized, we can see that matte black absorbs and emits heat most effectively. This is why radiators are often painted black. It helps them release heat efficiently into the room. Shiny silver, in contrast, reflects infrared radiation, making it a poor emitter. This property is useful in insulation materials, like survival blankets, which reflect body heat back toward you. Before ending the practical, let's remind ourselves: no experiment is perfect, so let's think about how we could improve our setup or identify potential errors. The intensity of radiation decreases as the detector moves farther from the source. Accordingly, keeping the distance constant ensures the readings are fair and comparable. Likewise, we need to ensure the cube is filled with enough water. Otherwise, the surfaces may not heat evenly. External heat sources or drafts in the room could also interfere with the results. By addressing these factors, we can ensure our data is as reliable as possible. Finally, working with hot water comes with risks, so let's stay safe. Remember to pour water carefully, using a funnel if necessary. Don't move the Leslie cube while it's hot. Hot surfaces can also burn, so handle the cube only after it has cooled completely. And that concludes our practical. Today we explored how different surfaces interact with infrared radiation, discovering that matte black surfaces are the best emitters and absorbers of heat. Shiny silver surfaces reflect most heat and emit very little. Surface texture and color play a crucial role in determining how materials handle heat transfer. This knowledge isn't just theoretical, it's the science behind insulation, energy-efficient design, and even the clothing we wear. By understanding the physics of heat transfer, we can make smarter choices in both engineering and everyday life.